Okay, so let's get to it. So number 3, let a and b be positive rational numbers such that square root of ab is irrational. Prove that root a plus root b must also be rational. Okay, so proof by contradiction. Let's suppose that a plus b is rational. In other words, a and b can be expressed in the ratio of integers where the denominator is non-zero. Since a and b are rational, we can write, so I mean, just to be, you can say a and b are rational. Right. A and b are rational, so you can say let a and b be, so just to be kind of nitpicky at this point, it's not really wrong, but just to be a little bit nitpicky, you'd say since a and b are rational, we know there exists m and uv and z, such that a equals blah and b equals blah. Okay. Okay. Because one thing that is a little bit incomplete is that you do need to say that these are integers, right, and that the denominators are non-zero, right? Because otherwise, what's the point, right? Your point is that a and b are rational, and so they can be expressed as quotients of integers. Okay, so you say it, right? And you justify it because you say since a and b are rational. Blah, blah, blah. Okay. Right? Or if you don't want to say that, you could also, another way people say is by hypothesis, right? By hypothesis. You could also say that, but I think that's sort of I prefer to be clear and just since a and b are rational, there's this, and then you b in the integers such that one. Okay. So then a plus b equals root a plus root b is this rational number, right? Okay. And so so a is m over n, right? So root a is root m over n, root m over n, right? Root b is root, that's fine, right? This is root a, this is root b, right? So what you're writing here is root a plus root b equals root ab, right? That's the justification, right? Since this, but then you say this, this plus this equals that, right? So what's the justification, right? Right now you have this plus this equals this, and there's a justification for it, right? But then you say this plus this equals this. Okay, and what's the justification for that? Why does that follow? Why does that follow from the above?
Are you with me?
Yes, I am. Why does that follow from the above?
Well, I had the square root of a plus square root of b equals xy because I'm assuming that x over y is rational.
Mm-hmm.
Then I just squared both sides.
Okay, so you square both sides, right? Square both sides. Square both sides, right? So you get root a plus root b, root a plus root b equals ab, right? So, yeah.
Why does root a plus root b equal root ab?
I'm sorry.
Yeah, how did that get wrong?
Yeah, what's that? What am I doing? No, that's wrong, right? Yeah. So, what are we doing? Sorry. We're trying to show.
Isn't it root a plus root b equals xy?
Equals xy, sorry. Root a plus root b equals xy. Sorry. Getting crazy. Sorry, thank you. Okay, so, yeah. Okay. So I'm trying to show how crazy you are, and instead I show how crazy I am. Okay, that's all right. That's why people work together. We stop each other from being crazy. Okay, So yeah, root a plus root b equals x over y. And then you're going to square both sides. What do you get? You get root a squared plus 2 root ab plus root b squared. Right? Root b squared equals x over plus. Right? Right. So you don't get this, right? But you get something else. Right? Right? Right. So this is an algebraic mistake. You squared both sides, but you didn't square both sides correctly. Okay. Right.
So this will be in terms of the n's and the n's and the v's, because I'm not in A world right now. Because
Yeah. So if we square both sides, what you're going to get is if you square both sides, so squaring both sides. You get this plus 2 root mu over root mv plus u over v equals x over y. Right? That's what you would get. Okay. Okay. So right. Suppose this were on an exam. Sometimes I would say, okay, let's go on and see how the rest of your argument goes. You know, given this this error, right? So you could say, well, let's see how the rest of your reasoning went. Let's do that, right? Just for practice, right? Just so. Suppose that were true, that when you squared both sides you got this, right? In that case, you combine these guys, and you would get that that equals the square root of that. This is a contradiction. Our rational number cannot be made from irrational numbers. Recall that the square root of ab is irrational. The square root of ab is irrational. Okay, I mean certainly the square root of ab is irrational, but how does that show that you're saying that this thing is irrational, right?
right, because AB, so that's the product of A and B.
Yeah. So
And
the square root.
XY is now in forms of products of the combination of A and B.
Okay, hold on 1 second. We know we're by hypothesis we know that square root of ab is irrational, right? Well, that's square root of ab is in your mn notation, the square root of mu and v. Right? So you know that this thing is irrational. Okay, but how does that? You're saying that that this thing is it. So if you got that this thing equaled that, then I would say sure, right? You've shown that this thing is irrational. You show that that thing is irrational. I'm sorry. If you show that. If you show that x over y equals this irrational number, then I'd say that's a good argument. But at this point, what you have, what you're saying is that this is irrational because this is irrational, right?
Yes.
Right? But that would require some justification. Why?
Well, I took off the pieces, so the square root of NV is in the square root of AB, and that's irrational. Is that no?
Okay, so so again, what you need to justify. You'd have to say why. Is it true that? So this way, I think you're making a lot of sort of jumps, but you're not justifying your jumps. Okay, so at this point. Say this is irrational, right? What you're saying is that here's your argument. You're saying that root AB is irrational, right? Our irrational, and then you're saying, basically you're saying, thus, here's what it looks like you're saying. You are saying, we know root AB, namely, this is irrational. So root MB plus UN over root MB is irrational. Okay, that's basically what you're saying, right? But you haven't justified this. So again, there's a big hole. Okay.
Well,
Yes.
in this regard, would a justification suffice if you show that the square root of NV is part? Because if you break up the square root of AB, you can have b square root of NU over square root of NV.
Certainly, yeah.
So then the pieces of an irrational function is irrational. So you can prove that, or you can extract that on the source statement.
Hold on one second. So you're telling me that if you have an irrational number, then it has to be expressed as a quotient of irrational numbers. Is that what you're saying? If it's irrational, then both the denominator and the numerator and the denominator have to be irrational?
Well, just one of them has to be irrational.
Okay, one of them?
Just one of them has to be irrational. Because you can't, we proved.
One of them has to be irrational?
Right.
Okay.
We proved in the previous questions that if you have the sum of a rational and an irrational, it gives you an irrational number. So you just only need one of them to be irrational.
Okay,
to be
okay.
irrational.
But how do you know that it's the denominator that's irrational?
You don't.
You don't? Okay, but you could assume that one of them is. So let's go on.
So if you assume that the square root of the NV is irrational, then the source statement is irrational by default. But if that's not the case.
Well, no. Hold on. Are you saying that if you have an irrational denominator, then that makes your number irrational?
That's the assumption I'm making.
Suppose I have the square root of 3 and I put on top of it the square root of 3. Is that an irrational number? No, right? Okay, so the moral is be pretty conscious. Make clear to yourself what your statement is. Okay, make clear to yourself what your statement is. Right? What you're stating here is that since this is irrational, right? Since this is irrational, this must also be rational, right? So I think that was a little bit not perfectly clear to yourself, maybe. I don't know how I don't know if it was or was not, but it seems to me by the writing that it wasn't completely clear what your deduction was. Okay, and then once you're clear of what your deduction is, see if you can make sure if it's not a trivial deduction that you can justify it. Right. So this requires this statement really requires some justification, right? Okay, really requires justification. And once you get into it, you'll see maybe it's not even true. Okay. Any comments from people? Maybe I should let you do the work of this. I think I should. So let's go to the second one. You're trying to show that the square root of 3 is irrational, right? So Edwin says let's do proof by contradiction, sort of following the famous argument of so and so, right? Assume that it is rational, and then it can be expressed as a over b when a over b are in z and b is not 0. Then square both sides, you get that 3b squared is equal to a squared. If b is odd, then b squared is odd. And so, what does this say? A and a squared. A and a squared? Yeah. A and a squared. A and a squared. This looks like a divides evenly into a squared to me. Yeah. Yeah. Don't use this notation. Ever. No, at least not in this class, and not in the math class. So a and a squared are also odd. If b is odd, then b squared is odd, and you've got a product of odd numbers which would be odd, which means that a squared is odd, so a is also odd. Okay, so that's true. Right, so this is by you know, I mean, if you want, you could say like, if a squared is odd, then so you might, you know, properly you should put in a little blurb of justification, right? That b squared odd implies 3b squared odd, since the product of odds is odd. Product of odds is odd, and then a squared is odd, and so since a squared equals 3b squared is odd, then a is odd also from last time. Right, so you know, justify what you're doing. Okay, so similarly, if b is even, then b squared is even. So b and b squared are also even.
Oh, I meant a and a squared there.
Oh, I'm sorry, a and a squared. Yeah, sorry. A and a squared are also even. Okay, so when they're odd, everybody is odd. When they're even, when b is odd, b squared, a and a squared are odd. When b is even, b squared, a and a squared are even. Okay. So when a and b are both odd, then we have this. Then a can be expressed as this, right, where n and m are integers. Right. So one thing, you know, when you introduce a variable, you want to explain what that variable is. Okay. You don't just want to say 2n. I would say, what is n? What is n, right? So you properly you say a equals 2n plus 1, b equals 2n plus 1 for some n and m in z. Okay, for some n, m, and z. Since so include this sort of word. Right, since, right? Don't just jump to this formula, or you know, sometimes you put a markup here. You put a markup here, and you say by star, you know, 3b squared equals a squared, right? So 3 times 2n plus 1 squared equals 2n plus 1 quantity squared, right? And then you multiply this thing out, right? 12n squared plus 12n plus 3 equals 4n squared plus 4n plus 1, right? And then, right, this is m's. These are m's on the left, right? These are m's.
Yeah.
Right, these are m's on the left. So then, what are you doing?
I subtracted 1 from both sides, and then divided by 2.
Okay, so you subtracted 1 from both sides, right? You divided by 2. Okay, great. Right. And then you say 2 times 3m squared plus 3m plus 1 equals 2 times n squared plus n. Okay. The left-hand side is odd. The left-hand side is odd. It's an even number plus 1. And the right-hand side is even. Therefore, there's a contradiction. Okay. So that's pretty cool. That's pretty cool, Edwin. I like it. But what's wrong with what's wrong here, or what's missing here? When A and B are both even. Why did you leave that case out?
I thought I was done.
You thought you were done. Okay, so yeah, you're not done, right? You said there are two possible cases. A and B are odd, either, when b is odd, everybody's odd. When b is even, everybody's even, right? So you've got two cases. Either a and b are odd, or a and b are even. That's the whole world to you. Those are the only two possibilities. You've done one, you haven't done the other. Okay. So you need to work out the other side and see that see if that works out. Okay. But in terms of writing, this is pretty. This is not bad. This is not bad. Yeah. Okay. 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 So I'll send out solutions later, take a look at the solutions to see a different way of doing these things. Okay. And if you find that if you find it difficult, that's okay. That's okay. Don't just keep on going, and things will get better, basically. Okay, so don't worry. When I first went to college, my first course was in linear algebra. Okay, but the course was out of a text called Finite Dimensional Vector Spaces. So it was actually a really theoretical course, probably comparable to 173 here. Yeah. Yeah.
What college did you go to?
Princeton.
Okay.
Yeah. So that's your first course. If you get if you scored well, if you did well in high school, then that's basically your first course. And so it was really shocking to me. This textbook on finite dimensional vector spaces, because the first words were, let F denote a field. Let F denote a field. A field satisfies the following axioms, and it laid out the field axioms. What is this? Yeah. So the professor. I remember very clearly. The professor coming in and writing up. He's from England. He said, suppose there's a field, and he started writing, and then he just kept on going. And I did very poorly, or at least I found it really hard to get this idea of what a proof was and this sort of thing. And so this course is sort of like the course that I wish I had at that time. Like I basically created this course, or the material for this course, by going back to my old notes at that time, going through everything and seeing all the misunderstandings that I had, and then trying to say, okay, let's clear that all out. Yeah, but it was really discouraging for me. And then I went to, just to drop names, the professor was Wiles, Andrew Wiles. He's the one who, Fermat's theorem. Yeah.
Who's your professor?
Yeah. So just to drop names. Yeah. So I've had the chance to be taught by great people. But he said this to me. So I went, professor, this is really hard. I just don't get this at all. And he said, don't be discouraged. He said, don't be discouraged. When I first picked up a theoretical textbook, I could not understand it at all. And so this is one of the great mathematicians of maybe all time, right? And so you think, okay, and I didn't realize at the time. I didn't realize this at the time that this was. This was before he had proved Fermat's theorem in any case. But he was already a great mathematician, of course. But in hindsight, for him, one of the somebody who will be remembered in 1,000 years' time if the human race still exists, then right? For him to say something like, don't be discouraged. When I first picked up a theoretical textbook, I couldn't understand it at all. That should be very encouraging, right? Right? That should be very encouraging, because then it's okay not to understand anything at all, right? As long as you keep going, right? So that was really inspirational to me, not because he was great, but just the idea, like, just don't be discouraged. Don't be discouraged. So keep on going. Yeah. yeah, having the chance to go to Princeton was great because you had the chance to interact with these really world-class people. So they were all, everywhere there are these world-class people. It's very inspiring. On the other hand, the system of education was sort of like, here's the bar, jump, right? Right? Here's the bar, it's up there, right? If you want to be like this, there's the bar. You've got to jump over that bar. And so like everybody's like, okay. And everybody like just starts jumping for the bar, right? But it's not. And if you fail to cross that bar, goodbye. That's it, right? There's nobody who's going to say, here, let me show you how to get up to that bar, or some trick of getting up to that bar, or here, let me help you up to that bar. No, it's like you have to figure out your way to get over that bar yourself. So of the 70 students who started out in that class, only 20 finished it. Right?
Well, that's why Princeton is breaking down.
Yeah, right. That's the way. That's one way. It's a different way from this way. Yeah. Okay. Okay. So let's go on. Okay. So yeah, and I don't regret that experience. It was extremely painful. It was extremely painful, and everybody just just studied their brains out. Just to give you, just to amuse you, people were working so hard, just like studying. Sometimes, past midnight, somebody would open a window and start screaming. And then everybody else would open their windows also and start screaming out the window. And then after a few minutes, it would pass, and then you get back to study. Okay, so, welcome to Princeton University. Right? People work hard. Really hard. Okay. Yeah, those were good times. Okay, so going back to what we were talking about earlier. So last time we gave that famous argument that root 2 is not rational. Okay, right. Now, right, root 2 is irrational. Right? Root 2 is an irrational number. Okay, so there's this whole, what you see is that the rational numbers, are missing some things, right? They're missing some things. In particular, right, it's missing, is lacking, at least, the solution to, x squared minus 2 equals 8, right? It's lacking this number, right? And this is what's called an algebraic number. So let me give a definition. X is called an algebraic number. Algebraic number if it solves a polynomial equation. Okay. Polynomial equation of the form, right? Something of the form a n x to the n plus a n minus 1 x to the n minus 1 plus a1x plus a naught equals 0, where ai are all in z and n is some natural number. Okay, so for example, right, root 2 is an algebraic number. Root 2 is an algebraic number because it satisfies this polynomial equation, right, with integer coefficients. Okay, right. This is a polynomial equation with has integer coefficients, right? Root 2 satisfies it. Root 2 is an algebraic number. Okay, so what we see is that Q is missing at least some algebraic numbers. Okay. At least some. Okay. So you might think, well, maybe the thing to do to fix up Q, we've been saying, what's the difference between Q and R, right? And we see that, well, if we were in R, we'd have the solution. We'd have this solution. So one might think, R is just Q with all real algebraic numbers adjoined. You might think that, right? But in fact, even if you throw in all the algebraic numbers, there's still a lot of holes. Okay, but in fact, that gets us nowhere near R. Nowhere near R. Okay. Even if you throw it in, there'd still be lots of gaps. Okay, there actually be gaps. Okay. Okay. So we're working our way towards R. So hopefully we'll get there shortly. Before we do, let me give the proof of the rational zeros theorem. So remember, in this section there was this thing called the rational zeros theorem. Okay, so suppose a and xn, a n. xn minus 1 plus a1x plus a naught is a polynomial equation with n greater than or equal 1, an not equal to 0, and a0 not equal to 0. Here's the statement. If R being P over Q is a rational number, is a rational solution to star with P and Q in lowest terms, right? No common factors. Then it must be that P divides A naught and Q divides AN. So this is the rational zeros theorem. Okay. Okay, so for example, we had this polynomial equation written up before, right? So if P over Q is a solution, is a rational solution of this, then we know, what do you know? That P has to divide evenly into 2, and that Q has to divide evenly into 1. Right? Okay, so what does that tell you? That P must be either plus or minus 1 or plus or minus 2, and Q has to be, could be plus or minus 1. Right? Okay, So assuming the theorem, assuming the theorem, if you have a rational solution, then you know what the denominator must be. You know where the denominator must be, and you know where the numerator and the denominator must be, right? And so, the only possible answers are P must be either plus or minus 1. If there is a rational solution, it has to be either plus or minus 1 or plus or minus 2. And you can check, and you say, oh, well, neither of those works. None of those works. None of those is a solution. So the solution must be, if a solution exists, must be irrational. Okay, so this is another way that you could show that the square root of 2 has to be irrational, right? The square root of 2 is something that satisfies this, and we see by the rational zeros that the only rational solutions of this would have to be plus or minus 1 or plus or minus 2. None of those is a solution, and so the solution of that must be irrational. Okay, so that's another way of proving the irrationality of root 2. Okay. Any questions? Any questions? Okay, so let's give the proof of the theorem. Actually, is everyone done copying this thing here? I'm going to erase it. Pam, are you done?
Yep.
Oh, great. So proof. Okay. So say that P over Q solves star, right? Yeah. We're trying to show that P over Q has some form, right? Let's suppose that P over Q solves the thing. Well, what does that tell you? Then, in other words, that A sub n P over Q to the n plus P over A sub 1 P over Q plus A not equals 0. Right? In that case, let's multiply through by Q to the n. So multiply by Q to the n on both sides. You get that A sub n P to the n plus A sub 1 P Q to the n minus 1 plus A naught Q to the n is equal to 0. So let me throw in the second term, just to make it clearer. Pn plus A n minus 1 P n minus 1 Q plus. Okay. Well then, moving everything else, all of these guys to the other side, and factoring out a Q, we get this A sub n P to the n minus 1 plus A n P Q to the n minus 2 plus A naught Q to the n minus 1. Okay. Okay. You observe, Q divides the right-hand side. So Q must divide A n P times Q to the n. Yeah.
How do we know that Q divides the left-hand side?
The right-hand side.
The left-hand side?
Oh, well, the right-hand side and the left-hand side are equal, right? They're the same
Yeah,
number.
but how do we know it's Q and not the other term?
So, just like here we've got two numbers, A and B. It's obvious from the form of B that Q divides B, right? Q definitely divides B, right? But B is A,
Oh.
right? So if it divides, one half of one side of an equality, it's going to divide the other half, certainly. Okay. And then what you use is that Q. So what happens then? Q divides a sub n p to the n. Okay. Then,
Oh.
yeah, Mia, what
Do
do you?
you know, since you said that P and Q have no common factors, that Q must divide A to the n naught?
Exactly. So Q has no common factors with p to the n, right? Because Q has no common factors with p, right? They have no common factors, and so if you divide two things and you don't divide this guy, then you must divide this guy. Okay, so that actually requires justification, but they refer you to another book, right? If Q divides AB and Q does not divide B, then actually Q divides A. So, yeah, that's sort of maybe intuitively clear, right? Mia, you felt like that's true. It is true. It requires a little bit of justification that we're going to avoid. Okay. We're not going to give it. But in any case, Q divides A sub n. Okay. And then okay, so what we've seen is that that Q has to divide A to the A sub n. Okay. So Q divides the lead term. The denominator must divide the lead term. Okay. Now our second part is we want to show. Second part, we need to show that A naught, that P divides A naught. Right? So how do you think we're going to do it? You've read the book. Somebody should be able to tell me. How do you do it?
You multiply by Q as Qn.
Okay, so multiply again by Qn, right? We get this guy again, right? And then what do you do with that?
Exactly the same.
Exactly the same thing, except you move.
P.
Yeah, you move everybody involving P to the other side, right? So you do the same thing. So as before, get A naught Q to the n equals negative P A sub n P to the n minus 1 plus plus A1 Q to the n minus 1. Right? So just move everybody involving P to the other side, and you get then that P divides the right-hand side, so P divides A naught. So there's a nice symmetry to this argument. Okay, so I don't think I'll use the last minute to start the new section. So that's it for today. I'll send out an assignment later. Yeah, that's it for today.